So, hello everybody, my name is Cyprien Hoelzl, and today I will be talking about onboard monitoring for railway infrastructure condition assessment. It's a project that we are doing together with SBB. They are supporting a lot, and we are looking to develop new ways to monitor the infrastructure. So the challenge behind this is that the increasing demand in mobility is one of the biggest challenges in Switzerland. And in the current times, it went a bit down, but now it is going up again, and probably in the end, the mobility will grow back to its former levels. And the rails or the infrastructure due to the trains is getting damaged, and the rails are making up a big part of the maintenance effort. And so to monitor the condition of the track, there are different inspection ways. There is the traditional inspection with track inspectors that walk on the track at regular intervals, but this is not the best way to go about. So nowadays there are diagnostic vehicles that support this effort. So vehicles that are equipped with many sensors to measure things such as longitudinal level using laser sensors and railhead images with cameras. And to further develop this, these industrial means are not so easy to operate. You cannot roll them every day. They need special drivers, and they need a lot of maintenance and personnel to keep them running. And onboard monitoring is, in a sense, the future we are currently exploring with low-cost sensors that could be on passenger trains. And there are several onboard monitoring trains in Switzerland, such as the onboard monitoring ICN, that we will be using data from. Using the previously mentioned railhead images, SBB has a project that can classify from the railhead images if there is an insulated joint, a weld, or a surface defect. And Ilir will give a talk a bit later today in the AI and industry track. The challenge is that these algorithms are not perfect yet, and in particular, they are not perfect on specific components such as insulated joints and welds. So welds may be defect or not, but the algorithm or visually it's not always so easy to tell the condition. So of the 80,000 welds on the network, which are crossed regularly by the monitoring vehicles and the onboard monitoring train, we want to tell what the condition is with accelerations. So there are these diagnostic monitoring vehicles as well as the onboard monitoring ICN that deliver us acceleration data from the axle and also from other elements of the vehicle. So there are different methodologies we explored within this project. So I will quickly go about the different methods we use to extract indicators from these accelerations before going to a case study we are currently working on for making these findings productive in a sense of bringing this information down to the asset manager and making the knowledge better. So one way is to use vehicle models, full order models or simplified models, and combine them with a Kalman filter to extract contact forces or geometric profiles. We also used the Volt-Kalman filter to extract information about the stiffness of the track. So around the sleeper passage frequency, we can relate the sleeper passage frequency amplitude to the subsidence measurement of SBB. So using this information, we can tell how stiff the track superstructure is. This is an important indicator, especially on the transition of stiffness. The maintenances go up a lot because when there are sudden stiffness changes in track, there will also be higher forces that will cause settlements of the ballast and damages on the rail. And using these labels that are provided from the visual systems, so we know where the surface defects, the welds, and the insulated joints are. And from these labels and the accelerations, we developed some classifiers using convolutional neural networks as well as random forests to classify if we now have a surface defect, a weld, or an insulated joint in our acceleration samples. This may be very useful going in the case of having onboard monitoring vehicles that need to predict it on the go and not transmit all the data back into the depot, which will make, or which already makes now petabytes of data in storage. And now, as I mentioned before, we have welds which we don't know the condition of, and we want to improve this. So there is a database of welds that we constructed using these labeled images. So for each crossing of a weld, we get an observation, so we have an image, and we can match these observations together in time to see how the images change. And we can also extract the corresponding acceleration data. Once we have the acceleration data, we can extract some indicators, such as the longitudinal level D0, which corresponds to an irregularity in the track roughness in a certain wavelength. D0 corresponds to short wavelengths from 0.5 to 3 meters. We can also extract acceleration-based features such as a discrete wavelet transform, and then compute features which we can then use to do extreme value analysis and outlier detection, and do expert evaluation and regression and prediction, so predicting the evolution into the future. So first, let me go over the extraction of indicators. What we have are images of railheads and time series of accelerations. During the crossing of a weld or a surface defect, some of these welds and most of these surface defects will feature a peak in acceleration and sometimes a dip in longitudinal level. So using the accelerations, we compute some features such as statistics, maximum, minimum quantiles, which are quite easy to explain and also to give to the asset manager to tell them, okay, there's something wrong. What is wrong? We observe a peak acceleration in this magnitude or a dip in this number of millimeters. So this is also something that can then be related to physical quantities that they can also observe outside in the field. Now going to extreme value analysis. Using the random forests, we determined that for the classification of surface defects and welds and insulated joints, the maximum acceleration and the minimum value of the D0, so the dip in D0, are the main indicators that connect to such a defect. The question now is, what is the threshold at which a weld would be defect, and what are the significant parameters defining a defect? To do such an analysis, we found a couple of instances, such as this weld where a breakout happened. So here you can see different railhead images of the same weld over time, actually over a couple of months between October 2020 and March 2021. And in before March 2021, there was a breakout on the rail. And due to this breakout, we got this information, but too late. So this was not detected by the image-based system. Now, with the accelerations and the longitudinal level, we can observe that before the deviation happened, we have low indicators. So we have values which fit in the distribution. The D0 value is already increased, which could hint at developing damage. but after the breakout, the values are quite high. And using these indications, we now gave outliers based on these different indications. In a sense, now it is not machine learning, but we want to generate information. So we fix an outlier threshold to give to the asset manager the images. So we have wells, but we don't know their condition, but we know that they react strongly in a dynamical perspective. What we are now doing is we get periodic measurements from the diagnostic vehicles, and these are then processed, and we detect these outliers in the wells. These are then given together with images of the railhead to in-office experts that can validate, that tell us, okay, now we see in the image something is defect or not. And then finally, in the cases where they also go out in the field to inspect these wells and take a picture and measure more in detail. So this goes into this feedback loop works together with people which are not necessarily data scientists, but experts in their field of inspecting the infrastructure and knowledge about the track. So using Excel, an image tool that we provide them, they can then label these images as defect or not defect. They can also use HTML applets with events shown individually or as heat map to detect specific regions that may feature problems or that may need improvement. And from this feedback round, we have first results. At increasing, so this plot shows the outlier score in function of the percent of deviations given a selected threshold. So for example, if at the current outlier score, 10% of the samples will be defect. If we go higher, a higher percentage of samples will feature a defect, a visually recognized defect. One limitation is that we are giving, or the evaluation is based on images from the railhead imaging system. High accelerations may not be visible in an image, so there might not be an issue on the rail visible, but in the geometry of the rail, which is not visible from the image. So we are still working on improving this, especially now that we have this information in the classification sense. Finally, I want to go over regression and prediction work. So we have these indicators that we can follow over time, and we want to detect an outlier as early as possible. So here you can see, for example, a track section with several okay wells, or wells with low accelerations, shown with green dots. And then we have a well that has high accelerations and that also features a deviation. And over time, we are following this progression, and we are fitting features to this growth, which we will, in the next step, also use as an input to give these inputs to the asset manager. And with this, I will come to the conclusion. So vehicle-track interaction is at the origin of fault appearances and growth on the track. We built an end-to-end validation chain to obtain information on the asset condition. And this shows already now good potential for early detection of weld deviation. This topic is also quite complex because we are working with vehicles with accelerations that have a lot of uncertainties that need to be dealt with. There are also uncertainties in the evaluation. Now we are working with over 10 different inspectors, and each of them will give their rating on their own wells in their own region. One thing you could think of is giving these wells in the different regions for multiple people validation. So not that one inspector validates only one specific weld, but that they validate each other's, and in this way also to be able to quantify the variance in this evaluation. And finally, now we are working on including this feedback to retrain now more advanced algorithms, such as Bayesian networks, to predict the damage in a weld. And these are also the first steps in sensor fusion between AESI, between the railhead images, and the axle box accelerations. So in the future, we will be going more and more into fusing different data streams. And with this, I thank you for your attention, and if you have questions, please ask them.
Thank you, Cyprien. Questions from the audience on this topic?
Oh.
Thank you very much for an interesting talk.
I can hear you, but...
So the question I have is actually, I was wondering how do you deal with I would say noise in the data when the train is actually changing the tracks? So the way you actually...
Switches, yes, we are excluding switches in these analyses. So we are only working on regular tracks. Switches are a whole topic in itself. So to simplify the work, it's always good to divide into specific topics. So when the train is switching between one track and the other, these segments, we know them, where they are located, and we exclude them. But also there we have done analysis where we see that from the samples that were seen in the condition logs and the switches that are defect, the switches that are defect correlate to the accelerations. So we can see a relation between this.
Yeah, thank you for the talk. I was a bit curious about false positives, right?
Mm-hmm.
How large workload is it, of these images? I presume you want to improve it, and so that's why you have the algorithmic work coming. But I mean, what kind of workload does this represent for the people looking at these? Do you have a lot of false positives?
You don't want too many false positives, but at the same time, you don't want too many false negatives. And it's always a challenging point. At what bar do you want to set the threshold to not overwhelm the people with information? And actually, of the wells that we had in this analysis, the last validation round was around November, and in the meantime, they replaced a lot of wells that we had in this analysis. So even the ones that they labeled as non-defect, in the meantime, are gone, or some of them are also now as defect in the database. So it is a challenge to have a threshold, not giving too much false positives, and we need to define at a certain point what is the quality necessary to make such a system productive. If it's not good enough, then you might have to think about, can this be made operational?
Hi, I was wondering if you could say something about the mapping of the different sensor data. So you have images taken by one vehicle, and then you have acceleration data by another vehicle, and somehow you have to map that it's the same event, the same location, right? That this acceleration data is correlated with this image. How do you manage to do that, getting that precise location of trains?
Yes, positioning is also a challenge. The positioning system on the vehicle is not too bad. It works with the track transponders, the Eurobalisen, which already gives generally a meter accurate position, but sometimes it can also be not so good in some cases. Now, to synchronize the measurements, we are using a point cloud correlation. So point cloud matching, we have these events that we match to each other using an algorithm that we can then use to detect the events accurately.
Thank you.
One last question for Cyprien. In case not, thank you for the interesting talk.
Thank you.